For a long time, we've thought of AI as, just a tool, a really smart search engine, maybe a text summarizer, just kind of sitting there waiting for us to tell it what to do. Well, today, we're going to throw that whole idea out the window. We're talking about a massive shift in what AI is becoming.
Yeah, let's really dig into this quote because it's the heart of everything we're talking about. These AI systems are moving way beyond just being digital assistants. They're coming up with their own hypotheses. They're designing experiments, and get this, they are debugging their own thinking, all without a human constantly looking over their shoulder.
So how does this actually play out in the real world? Well, it all kicks off with a story that honestly sounds like it's straight out of a sci-fi movie. But this is a real documented case of an AI acting less like an assistant and more like something else entirely.
So here was the setup. A team of expert researchers gave an AI a genuinely difficult biology question. They basically asked it to figure out why these things, they're called CFPICs, but you don't need to remember that, why they show up across so many different types of bacteria. So the AI gets to work, crunches all the public data out there, and comes back with a brand new hypothesis, completely on its own. It proposed that these CPICs connect with the tails of different viruses, and that's what allows them to infect a much wider range of hosts. A really complex, specific scientific idea. And this is the stunning part. A human research team had already proven that exact same idea was correct in their lab, but their results weren't published yet. The AI reached a verified scientific discovery all by itself. It wasn't an assistant, it was a parallel discoverer. So the big question is, how on earth is that even possible?
Look, the answer here isn't some kind of magic trick. It all comes down to architecture. To really get how the AI pulled this off, we have to pop the hood and see how these systems are built to basically mimic the entire scientific process.
Now, what's really fascinating here is that this isn't one single giant AI brain. Nope, it's actually designed more like a research team. You've got one agent that's an expert at digging through literature, another that's great at synthesizing information, one that proposes new ideas, and maybe most importantly, you've got a built-in skeptic whose only job is to challenge all the assumptions.
And this AI team, they don't just run with the first idea they have. Oh no, skepticism is baked right into their code. The system generates dozens of potential hypotheses, and then it makes them fight. It stages a simulated scientific debate among its agents, challenging each idea, forcing them to compete until only the most solid ones survive.
This whole internal showdown has a name: tournament-based evolution. And it's exactly what it sounds like. Think survival of the fittest, but for its scientific ideas. It's the system's way of making sure that the final hypothesis isn't just a lucky guess, but an idea that has survived some intense internal grilling. Okay, so we've got this team of AI agents debating ideas, but how do these agents actually reason through such complex problems? This gets us into the real engine room of the AI's cognitive architecture. Until pretty recently, AIs used what's called chain of thought. You can think of it like having to write out every single step of a math problem on a whiteboard. It works, but it's slow, and if you make one tiny mistake, the whole thing just breaks. The new frontier is latent reasoning. This is more like doing the math in your head. It's way faster, more efficient, and it allows for long, coherent trains of thought silently inside the model. And the foundational tech that makes all of this possible is, of course, the transformer. Its self-attention mechanism is the magic sauce that lets the model connect the beginning of a long scientific paper with the very end. It doesn't lose the plot. This creates the long-term understanding that's absolutely essential for this kind of deep scientific planning. But wait, if these systems are so good at thinking, we have to talk about the elephant in the room. The massive, well-known flaw that this entire conversation hinges on: trust. This brings us to the single biggest hurdle for AI in any high-stakes field. So here's the thing you absolutely have to understand. Hallucinations aren't a bug, they are a feature of how these models are built. They are designed to predict the next plausible word, not necessarily the next true one. And that means they can, and absolutely will, just make stuff up with total unwavering confidence. So what does that mean for science? It means relying on a model to verify itself, to grade its own homework, is a complete non-starter. You just can't do it. Which means you have to build in an external, mandatory system for verification. Okay, so if the model can't be trusted on its own, what's the fix? Well, you have to build in safety nets, and that's where these self-correction loops come into play. These are architectures designed for one specific reason: to catch and fix the AI's own mistakes. That's a fair question, right?
It's one thing to say you've built a verification system, but it's another thing entirely to prove that it makes a real, measurable difference.
Well, here's the data from just one of these frameworks, called Reflection. Just by adding this self-correction layer, performance on decision-making tasks jumped by 22%, and on reasoning tasks by 20%. I mean, these are not minor tweaks. This is a significant, measurable boost in reliability.
So how do they work? Well, the Critic framework, for example, uses external tools, like literally Google Search, to constantly fact-check the AI, yanking it out of its own head. And the Reflection framework acts like a journal. When a plan fails, a separate model analyzes the mistake and creates an episodic memory, so the system learns from what went wrong and won't do it again. And all of this leads to a really powerful conclusion. In these high-stakes systems, reliability isn't something you just hope for. It's an architectural feature. It has to be engineered into the system from the ground up, with mandatory, multi-layered loops of verification.
So let's zoom back out. When you combine this internal, in-your-head reasoning, the multi-agent teamwork, and these mandatory self-correction loops, what you really get is the blueprint for the future. It's not about humans or machines. It's about a super powerful, high-throughput scientific partnership between them.
Which leaves us with one final and, I think, critical question. If these autonomous systems can continuously optimize their own reasoning, apply critiques, and drive discoveries faster than any human team ever could, what's our role? What becomes the most critical, uniquely human part of doing science? That's something to think about.